Jim, I'm very pleased to talk with you about your book, Mass. It was a pleasure to be the translator. I am your translator into Romanian. Hope it's a good translation. Now I want to say a few words about you. After the discovery of the Higgs boson, I received the Humanitas Publishing House several books about the Higgs boson, and I chose your book instantly because it was the best book, and you have the talent to explain complicated things in a very simple manner. Then we translated your origins, and you gave a talk at the Humanitas conferences, Ateneu Roman. And now we have this third book of yours. I want to start the discussion about your book, speaking a little bit about your approach. Because, you know, something shocked me at the very beginning. It's a book about matter, what matter or substance or what matter is. Now, of course, you started with the Greeks, with the ancient Greeks. But generally in such books, the author starts by explaining the ideas of Democritus and so on. Mm-hmm. But no, you did something very interesting. It is interesting for your approach. You are supposing we are taking a walk near the sea, and we see a lot of things. We see a boat, we experience the wind, we see the sand, and so on. So you explain what can be understood by observing and by making some judgments, some rational judgments, using both observation and logic. I think this is here is the deep structure of your approach. I see you are putting yourself in the shoes of the reader. You are not speaking as someone who knows everything and who teaches. Am I wrong? Is it your approach? This is the basic idea of your approach?
That it was the basic idea. One of the advantages, I think, of starting with the ancient Greek atomists was to try to get a sense of what you do as an individual when you don't have a laboratory. You can't do experiments beyond some fairly rudimentary experiments. And so all you have is your ability to, as you say, observe and draw some logical conclusions from what you observe. And I've always been struck whenever I've read about the ancient Greeks as to how much they were able to deduce just from simply observing and applying some logic. Now, of course, you know, you can only go so far with that. And the book, it moves on to, it jumps several centuries because there wasn't a great deal of progress, frankly, made between the ancient Greeks and the beginnings of the origins of science with Newton and later John Dalton. But you could see how some of the threads of what the ancient Greeks had been able to deduce for themselves still found their way into what we would now regard as classical modern science. And that's always fascinated me. And the other device that I thought might be helpful in this exploration was a device I've seen used in newspapers in the UK in the past, and that's to summarize effectively each chapter with kind of 5 things we've learned. So looking a little bit back to say, in 5 bullet points to summarize, I felt that was quite a useful device as well for those that readers that might struggle with certainly some of the more esoteric concepts towards the end of the book, I felt that was a useful device to a ready reckoner, if you like, so that you could keep track of where we've got to in the story.
Right. In the meantime, you are dealing with quite technical things. Yeah, and it's I admit I admire you for your capacity for your ability of explaining such intricate, delicate problems. But for instance, you are giving a very good description of what happens with the Higgs boson.
Mm-hmm.
It's a very intuitive way of understanding how things gain mass.
Mm-hmm.
And also you are giving a very not simple, but very intuitive description of what happens in quantum electrodynamics or in quantum chromodynamics.
Yes. Yeah. So yeah, these are always going to be challenging subjects to popularize, and I'll be the first to admit that there are some excellent books out there that any interested reader can consult, where they may learn maybe more than they can learn from books that I've produced in the past. I tend to try to find a middle road. You can use analogies, you can create visual images which convey something of the nature of the physics to an interested reader without the scientific background to appreciate all the subtleties necessarily. And I have found in the past that some of those abstractions, those images, they're now getting so far away from the physics as to be, for me at least, unhelpful. So I try to create, if I can, a view, an impression of the physics that stays a little closer to the physics. I think what we have to understand that we're in a world now, in terms of our understanding of fundamental physics in quantum mechanics and in special and general relativity, where it's actually not intuitive by its very nature. It's not easy to grasp. And for me, that was actually part of the story that I wanted to tell, that a concept as seemingly obvious to us and apply a little bit of common sense as the ancient Greeks did 2,500 years ago, and you can deduce quite a lot about matter and its inherent property of mass. But what foundational physics has discovered through the 2,500 years that have passed in between is that the property of mass has in effect disappeared. It's become almost a phantom. It's as Einstein very, very cleverly pointed out way back in 1905, mass is energy divided by c squared. So what we think of as mass, an inherent property of material substance, is actually energy, and energy is a lot less tangible than mass. And I would argue that what we see now is actually a behavior of elementary particles like electrons and quarks and other things, as much as it is a property of those things. It's become what in philosophy we call a kind of secondary property. It's like color. It's something that we experience and we interact with it, and we have the consequences of dealing with particles that have mass. But if you're then trying to point to where that mass is at any time, at any moment, in all of these different interactions that are going on that makes up the visible universe, then you'll really struggle. What you'll have is a set of behaviors that we translate in our experience to the property of mass. So the whole point of the book was to try to lead the reader gently through the development, the evolving science from the ancient Greeks through Newton and Dalton and Cannizzaro and others, all the way through to our present understanding in foundational physics. And for me, it's part. I think it was my early interests in quantum mechanics that led me to become fascinated by these foundational concepts. If you look at our current understanding of space and time and of matter and light, then for sure we know a lot, but I have now come to the considered view that these are the concepts that form the backdrop onto which we build modern physics and our modern understanding of the universe and material particles in it. But my feeling is that our grasp of space and time and matter and light is probably as slippery as it was even to the ancient Greeks 2,500 years ago, and maybe that's our human dilemma. We can advance science, of course we can advance, we can push, we can make new discoveries, we can build more colliders, we can send up more satellites, we can explore the universe in greater detail. But my instinct now is that in 100 years' time, our understanding of space and time and matter and radiation will be more developed, but it'll still be just as slippery.
Now, if I'm trying to summarize in a way your book, to see the script of your book, yes, I would say that you are starting with something which is something tangible. Yeah, yes.
Yes.
The things we can perceive directly with our senses, and of course we are using also our minds. But you are starting with the tangible things, and at the very beginning, the mass seems to be the most tangible thing. Yeah. And now and then you are watching the evolution of the physics, of the physical theories. Yes. And you have Newton, you have Einstein, you have quantum mechanics, quantum electrodynamics, quantum chromodynamics. And it's very funny because using this not E equal mc squared, but m equal
E over c squared.
Over c squared. At the end, you find that at the beginning, if you say E equal mc squared, you say E is something a little bit slippy. What's energy?
Yeah, yeah.
But while using this approach by quantum fields and so on, the slippy property begins to be the mass and not the energy, because the energy, we can treat the energy by our theories. And it's a sort of, you are creating it's a reversed image you finally gain. You finally obtain.
Yeah,
I think this is the script of your book.
Yeah, and that sounds hopefully interesting, if not fascinating. But I think the point to make is that this is very much the conclusion of deep, detailed quantum chromo. Well, it's something called LCD. It's effectively a kind of version of quantum chromodynamics which lends itself to computer calculations. Now, these are still supercomputer calculations, so these are very, very involved. They require a lot of number crunching in order to be able to get answers. And one of the prompts for me to start thinking about this book was the publication of research papers on the composition of the neutron and the proton, effectively with quantum chromodynamic calculations of where its mass comes from. The Nobel laureate Frank Wilczek has spoken also about the idea of mass without mass, which is where the book finishes. So this is not some fantasy, where we create this mirror E equals mc squared going to m equals e over c squared. In fact, that was E equals mc squared doesn't appear in Einstein's 1905 paper. The equation appears as m equals e over c squared. But I was very much taken by these calculations, the results of these calculations, because it's one thing to speculate that the proton and the neutron, which are effectively the sources of mass for all atoms in the universe, including atoms that make us up. It's one thing to speculate. It's another thing to be able to then apply quantum theories like quantum chromodynamics and be able to actually demonstrate through a calculation that this is indeed the way it seems to work. And make no mistake, although quantum chromodynamics is a well-founded theory, it's part of the standard model of particle physics. The fact of the matter is it's not easy to apply. It's not easy to use. It's much more difficult, hence the need for supercomputers and different calculational methods in order to be able to make any progress. The fact that we've got to this point, I think, is something of a triumph. It's not necessarily research publications that are going to attract a lot of attention. And I thought, well, actually, if you put them in the context of the story of our unfolding understanding of the nature of matter and the concept of mass, that actually might make for a compelling story.
But you are finishing your book, not really finishing, but at the end, with a story, with something also very tangible, with the story of an ice cube, 1 inch, and with trying to see where the mass is coming from. And you are ending by saying everything is inside the protons and the neutrons, and it's not concerned with the mass of the quarks, but it has something to do with the energy of the gluons, connecting everything there. So you see, it's, the mass disappears miraculously.
And again, the idea of a cube of ice again was as you pointed out, wanting to make this a little bit more accessible and tangible for a reader. Any reader can go and pluck a cube of ice from the fridge, hold it in their hands, and then logically speculate on where its limited weight or mass comes from. But that device also gave me an opportunity, of course, to link back as well, because one of the most important of the early, not actually in this case Greek, but Roman philosophers, Lucretius, spoke of atoms of water being round because they were smooth. They had to, water flows, ice is slippery. So that gave the sense of atoms being round and moving and rolling over and on top of one another. Perfectly reasonable, logical conclusion just based on the properties of the material that you're examining. And how we go from that to the actual nature of the molecular structure of water, H2O, to hydrogen atoms, one oxygen atom, the development of our understanding of atomic theory, which meant that each atom has a nucleus. In the case of a hydrogen atom, it's a single proton. In the case of an oxygen atom, it's a more complex mix of protons and neutrons. But add all of these protons and neutrons together, and you've got the mass of a water molecule, and so on. And you go, and then you go into subnuclear physics, that is obviously developed after the war, and you get this unfolding realization that in fact that the closer you look, if your idea as an atomist was to strip everything down to smaller and smaller and smaller and smaller constituents, logic says that there's probably a point at which you either hit rock bottom, you come down to the elementary stuff that everything is made of, or it slips like liquid mercury. It slips out of your grasp completely, and what you're left with is something that's more bizarre, but nonetheless, I think in many ways more satisfactory as a conclusion for what sits at the base of everything. And that is this notion of the energy of particles flitting back and forth within a proton or within a neutron. It's not just the gluons; it's the quarks.
Yes,
I can't picture what these things might look like
the energy
inside a proton. Yeah, but this is it's uncomfortable. It's a very uncomfortable environment, and there's a lot of energy created from some very, very light particles. Gluons are massless, like photons. Quarks are very, very, very light particles. Their mass comes, as you've said, from the interaction with the Higgs field. So the mass of a proton and mass of a neutron, which are much, much heavier, comes from the fact that these things sit very uncomfortably inside these host particles.
Now, while you were speaking about the atomists, I remember the idea of Feynman said once that if he is supposed to summarize everything physics gives us, he would summarize in this sentence: everything is composed by atoms. Mm-hmm. And this would be in one phrase, in one sentence, he would say, this is the essence of physics, of what the physics teaches us.
Yeah.
But in the meantime, I think your book is not treating almost everything. You are speaking about the classical mechanics, a little bit about chemistry.
Yeah.
Because you have also a chemist background.
Yeah.
You are speaking about relativity, special and general relativity, quantum mechanics, quantum electrodynamics, quantum chromodynamics. You have here in this book, you have all the physics.
The whole of physics, yeah.
And it's, I must repeat it. You are able to say very complicated things, very subtle things about symmetries and about Higgs boson and so on, in quite simple images. And it's your gift.
Well, I mean, I acknowledge a singular contribution to the writing of the book in the book itself, but I can make the point here that I actually have to thank my mother, of course, for lots of things. But I asked actually if she would be interested in. She's touched, I think, and looked and tried to read some of my books in the past, and I said, "Would you be interested in looking at the manuscript? It's something that I know that she's quite interested in. Would you be interested in looking at the manuscript as I write it and coming back with comments?" And so the comments would come back with, "Well, why have you written it like this? Why don't you write it like that?" So her input actually also, hopefully, is what the reader can sense as being a way of just easing off. I do write more complex sentences than are really required sometimes, and it's good to have someone looking over your shoulder saying, "Nah, you can say that in a simpler way."
So it's like writing this book for your mother.
Yes, very much so. I mean, of course, she has no scientific training, no scientific background, so there were going to be bits of it that. So my question to her really was to say, look, if there's stuff you don't understand, there's maybe a sense in which I can fill in a little bit more background to help it become a little bit more understandable. But there comes a point where you have to a certain extent accept and allow it to flow over you. If you're not going to get the esoterics of quantum chromodynamics or LQD or whatever it might be, then to a certain degree you need an ability to accept it and move on. And to a certain extent, I think that's required of the book as you go, maybe you get towards the end.
Thank you very much, Jim. Hope to see you in Bucharest after the COVID crisis.
I look forward to being there again one day.
and hope to publish your books.
Okay, fantastic. Thanks, Vlad.
Thank you very much, Jim.